Good morning everybody, hope you're all healthy and safe. So let us continue with our theorem. So I had stated that we'll be focusing on a main proposition and we have to do a few lemmas before that. So one we have completed and in that lemma we had seen that for any operator, positive operator, we can find another positive operator, non-negative operator, such that x square is equal to a, and also if they commute, that is if two operators commute, ab is equal to ba, then root of ab is also equal to root a into b is equal to b into root a. So this is what we had proved, and we had proved a small corollary related to that. So again in this lecture of section 6.3 we'll be discussing another lemma which states the property of which uses the lemma that we have just now seen or just now proved. That is, the lemma is as follows. That is, if a and b are non-negative and ab equal to ba, then ab is also non-negative. This is what we have to prove. Okay, so the proof is simple. With the help of the previous lemma we can easily prove this. What we have two non-negative operators, and we have to show that if they commute, then the corresponding product will also be non-negative. So let's see. We have by previous lemma for every a greater than equal to 0 and b, if ab equal to ba, then root a into b equal to b into root a, right? So let's see if ab is greater than 0. To prove ab greater than equal to 0, so for that I'll be evaluating the inner product ab of x comma x. Okay, so I can write this as inner product. Instead of a, I can write that as root of a into b x, right? A can be written as root of a into root of a. Now so I have, this is root a b x comma root a x. Okay, so this root a into b can be written as b into root ax, right? Okay, so I'm writing this as inner product b y y, where y is equal to root ax. Okay, now is this greater than or equal to 0? That is definitely greater than 0 because b is non-negative. Since b is non-negative, inner product b y y will be greater than 0. So I get inner product a b x, x is greater than 0. So this implies, what do I get? a b will be greater than equal to 0. That is, a b is non-negative. So we have proved that if a and b are non-negative, then the corresponding, and if they commute, then the corresponding product is also non-negative. So with the help of this we shall be proving the next proposition, that is proposition 6.3.3. It states that let a be such that mi is less than equal to a is less than equal to capital Mi for some m comma n belongs to R. Okay, and let p be a polynomial such that p of z is greater than equal to 0. That is, p of z is also non-negative, positive, that is, it has a non-negative coefficients. P of z is greater than equal to 0 for every z belonging to the interval m comma m. Okay, then p of a is also 0. Okay, so this is what we have to prove. So in this we'll be using the to prove this we'll be using the lemma that we have just now seen. Okay, so let's see how we can prove this proposition using the lemmas that we have proved. So for just remember the cycle. That is, first to prove the lemma that we did today, we had to use the previous lemma. So these two lemmas are required for the proof of this proposition. Okay, now given p of z is greater than equal to 0 for every z belonging to the interval m comma capital M, then the polynomial in p of z has the following form. Okay, that is, p of z is equal to some constant into the product of z minus alpha I, where alpha I is less than or equal to small m, into product of z beta I minus z, where this beta I is greater than or equal to capital M, into the quadratic factors, that is z minus gamma I whole square plus delta I square. Gamma I and delta I belongs to R. Okay, that is the p of z. We are choosing just that the p of z is a polynomial, right? The only condition is that it is greater, it is non-negative for z belongs to m comma m. So any polynomial, they can be factorized into the corresponding roots, right? So I have a constant c, and this is a general form, that is, it is the product of z minus alpha alpha I, where alpha I is less than equal to m, and beta I minus z, where beta I is greater than equal to m, and all other quadratic factors. So the linear factors and the quadratic factors come, and this gamma I delta I will represent all other roots in the real numbers. So p of z can have enough roots in real numbers. So we are just specifying the case of the interval m comma m. So it generally has this particular form. Okay, so now let's see what will be p of a. What will be p of a? Instead of z, we have to replace it by a, right? By alpha I less than or equal to m, a minus alpha I into product of beta I greater than or equal to m into beta I minus a, and into product of gamma and delta I belongs to set of reals into a minus gamma I square plus delta I square. Okay, so this is our p of a. Now we are given that small m into I is less than equal to a less than or equal to capital M into I, right? So from this, what do I get? I get a minus small m I is greater than equal to 0, and capital M I minus a is greater than equal to 0. Okay, that is, a minus mi is greater than equal to 0, and capital Mi minus a is greater than 0 for some m comma m belongs to R, right? So we can say a minus alpha I into I is greater than equal to 0, and right, m is like beta I minus a. Instead of small m and capital M, I'm replacing it by alpha I and beta I. So that is a minus alpha I into I is again alpha I. Okay, so this square will also be, sorry, alpha I a minus gamma square will also be greater than 0, and we can say that delta I square I is also greater than 0. So this implies I get a minus gamma I whole square plus delta I square I will also be greater than 0. So actually the terms that we have seen in P of A, everything will be greater than 0, right? All these operators will be greater than 0, and if you take their product, that is A into B. So let me just I'm not taking everything, I'm just showing you one. A minus alpha I into beta I minus A. What will this be? This is equal to beta IA minus A square minus alpha I beta I plus alpha IA. Now see what is beta I minus A into A minus alpha I. What is this? This is again the same thing, beta IA minus A square minus alpha I beta I plus alpha IA. So these are equal. So we have got non-negative operators which commute, right? Are you getting the idea? These two operators, they commute, and similarly we can show that they commute with all other operators. Okay. All other operators commute with each other. You can just verify that. Okay, so we have got the non-negative operators which commute with each other. So by the previous lemma, their product will also be greater than 0, right? Hence by previous lemma, their product is greater than or equal to 0. So what do we get? P of A will be greater than or equal to 0. Okay, so I hope the proof is clear. We have seen that first of all we express the given polynomial in the general form, keeping the roots and everything together, and we use the fact that mi is less than or equal to capital Mi, and from that we get two non-negative operators, that is a minus small mi is greater than or equal to 0, and a mi minus capital Mi minus A is greater than or equal to 0. And with the help of that we can see that what we are dealing is actually with non-negative operators, and also we can verify that they are commutative. So by previous lemma we can easily prove that the product of these operators will also be non-negative. Okay, so this was the proof of the proposition. So for this proposition we had to use the lemma that we did in today's lecture, and to prove the lemma that we did in today's lecture we had to use the previous lemma. So that is the proof of this. Now we shall see a small corollary related to it. So this is corollary 6.3.7. So that is, let A be such that Mi is less than or equal to A less than or equal to capital Mi for some m comma m in R. So this is the same condition which is given in the proposition. Now we are having two polynomials, P1 of t and P2 of t, with P1 of t less than or equal to P2 of t for all t element of m comma n. Okay. Then we need to show that P1 of A is less than or equal to P2 of A. So I hope the idea is clear. If you see, if you consider this polynomial, this is P1 of t is less than or equal to, given to us P1 of t is less than or equal to P2 of t, right? So this implies, what can I say, P2 of t minus P1 of t is greater than or equal to 0, right? Or I can write this as P2 minus P1 of t is greater than or equal to 0 for all t element of m comma n. So is there anything different in the condition? So then by proposition, the proof is simple. I'm just writing it over here. You might have already got the idea. proposition 6.3.3, what do I get? P2 minus P1 of A will be greater than or equal to 0. Hence, P1 of A is less than or equal to P2. So the corollary is very much simple of this proposition. So that is the end of our section 6.3. We have dealt with the non-negative operators and certain proposition and lemmas related to the same. So with this we shall wind up today's lecture. So thank you, stay safe, stay healthy.